Hi class, how are you today? I estimate that for about 75% of you, I should respond, "That's great!" Plus or minus about 2.5%. Alright, so the learning target for today is to be able to compute confidence intervals for p and compute the sample size used in estimating p. For the scale, you're a 3 if you can compute confidence intervals for p and compute the sample size used in estimating p. 2, you can compute confidence intervals for p and compute the sample size used in estimating p when the point estimate is known. 1, you can compute confidence intervals for p or compute the sample size used in estimating p when the point estimate is known. And 0, you cannot compute confidence intervals for p or compute the sample size used in estimating p when the point estimate is known. Let's get started. Section 7.3. Estimating p in the binomial distribution. What if that duck is wooden? I bet it's a wooden duck. Focus points. Compute the maximal length of error for proportions using a given level of confidence. So that's the margin of error. Compute confidence intervals for p and interpret the results. Interpret poll results. Compute the sample size to be used for estimating a proportion p when we have the estimate for p, and compute the sample size to be used for estimating a proportion p when we have no estimate for p. So you see on here we have interpret poll results. That's very important for this lesson because you'll see on the news or newspapers or on social media, there'll be lots of poll results like 73% of people do this, 85% of people do this, and how those are estimated and reported are going to be what we're dealing with today. The binomial distribution is completely determined by the number of trials n and the probability p of success on a single trial. For most experiments, the number of trials is chosen in advance. Then the distribution is completely determined by p. In this section, we will consider the problem of estimating p under the assumption that n has already been selected. So remember, binomials are between two choices. You're either doing the probability of something happens or the probability that something doesn't happen. We're employing what are called large sample methods. We will assume that the normal curve is a good approximation to the binomial distribution, and when necessary, we will use sample estimates for the standard deviation. Empirical studies have been shown that these methods are quite good, provided both np is greater than 5 and nq is greater than 5. Again, like usual, q is 1 minus p. Let R be the number of successes out of n trials in a binomial experiment, just like every other binomial experiment. We will take the sample proportion of successes p hat equals R over n as our point estimate for p, the population proportion of successes. So that's in our sample, we get a p hat, a sample proportion, and we want to use that as our estimate for the population proportion. So the probability of all of a specific type of population. So the point estimates for p and q are p hat is R over n and q hat is 1 minus p hat. As usual, n is the number of trials, R is the number of successes. So to compute the bounds for the margin of error, we need some information about the distribution of p hat values for different samples of the same size n. It turns out that for large samples, the distribution of values is well approximated by a normal curve, with the mean mu, but in this case p, and standard error being the standard deviation, the square root of pq over n. Since the distribution of p hat is approximately normal, we use features of the standard normal distribution to find the bounds for the difference p hat minus p. Recall that the critical value, z sub c, is the number such that an area equal to c under the standard normal curve falls between the negative critical value and the positive critical value. Then in terms of the language of probability, we've got the probability of negative z sub c times the standard deviation, square root of p2 over n, is less than p hat minus p is less than z sub c times the square root of p2 over n, and all of that should equal c. So the percent that we're looking at. Equation 17 says that the chance is c that the numerical difference between p hat and p is between negative z sub c times the square root of p2 over n and z sub c times square root of p2 over n. With the c confidence level, our estimate p hat differs from p by no more than e is equal to z sub c times the square root of p2 over n. So e, remember, is the margin of error. So with our point estimate, we're saying that there's a c percent chance that our point estimate is within the margin of error. As in section 7.1, we call e the maximal margin of error, which I just said. So the optional derivation of the equation, so this is how we can get the equation we were just dealing with. First, we need to show that p hat equals r over n has a distribution that is approximately normal with mu equals p and sigma equals square root of p2 over n. From section 6.6, we know that for a sufficiently large n, the binomial distribution can be approximated by a normal distribution with mu equals np and standard deviation sigma equals square root of npq. If r is the number of successes out of n trials of a binomial experiment, then r is a binomial random variable with a binomial distribution. When we convert r to standard z units, we obtain z equals r minus mu over sigma, which equals r minus np over square root of npq. For sufficiently large n, r will be approximately normally distributed, so z will be 2. If we divide both numerator and denominator of the last expression by n, the value of z will not change. So z equals r minus np over n, which is all over the square root of npq over n. Simplified, we find z equals r over n minus p, which is all over the square root of pq over n. Equation 18 tells us that the p hat equals r over n distribution is approximated by a normal curve with mu equals p and sigma equals square root of p2 over n. The probability is c that lies on the interval between negative z sub c and z sub c because an area equal to c under the standard normal curve lies between negative z sub c and z sub c. Using the language of probability, we write the probability that negative z sub c is less than z is less than z sub c equals c. From equation 18, we know that z equals p hat minus p over the square root of p2 over n. If we put this expression for z into the preceding equation, we obtain that the probability that negative z sub c is less than p hat minus p over the square root of p2 over n is less than z sub c equals c. If we multiply all parts of the inequality by the square root of p2 over n, we obtain the equivalent statement which we started with, which was the probability that negative z sub c times the square root of p2 over n is less than p hat minus p is less than z sub c times the square root of p2 over n, all equals c. So what we just did was we just derived this equation based on everything we previously know. So this is just how the equation is derived. Now we're going to get into more on how to use this equation and how it makes sense. To find a C confidence interval for P, we will use E in the place of the expression Z sub C times the square root of P2 over N in equation 17, just because saying that all the time gets annoying. No, that's not the real reason, but it's just easier. Then we get the probability that negative e is less than p hat minus p is less than e equals c. Some algebraic manipulation, which is subtracting p hat from both sides and multiplying both sides by negative 1, produces the mathematical equivalent statement: the probability that p hat minus e is less than p hat plus e equals c. Equation 20 states that the probability is c that p lies in the interval from p hat minus e to p hat plus e. Therefore, the interval from p hat minus e to p hat plus e is the c confidence interval for p that we wanted to find. There's one technical difficulty in computing the c confidence interval for p. The expression e equals z sub c times the square root of p2 over n requires that we know the values of p and q. In most situations, we will not know the actual values of p or q, so we will use our point estimates, where p is approximately p hat and q equals 1 minus p, which is approximately 1 minus p hat, to estimate e. These estimates are reliable for most practical purposes, since we are dealing with large sample theory, where NP and NQ are both greater than 5. For convenient reference, we'll summarize the information about C confidence intervals for P, the probability of success in a binomial distribution. So consider a binomial experiment with n trials, where P represents the population probability of success on a single trial, and Q equals 1 minus P represents the population probability of failure. Let R be a random variable that represents the number of successes out of the n binomial trials. The point estimates for P and Q are that P hat is equal to R over n, and Q hat is 1 minus P hat. The number of trials, n, should be sufficiently large so that n times P hat is greater than 5 and n times Q is greater than 5. Q hat. N times Q hat is greater than 5. The confidence interval for P is P hat minus E is less than P, which is less than P hat plus E, where E is equal to Z sub C times the square root of P hat times Q hat over N, which is equal to Z sub C times the square root of P hat times 1 minus P hat over N. C is the confidence level, where 0 is less than C is less than 1, and Z sub C is the critical value for the confidence level C based on the standard normal distribution. See table 5b of appendix 2 for frequently used values, or you can just look in the front of your book in the lower left-hand corner of the flappy thing. Suppose that 800 students were selected at random from a student body of 20,000 and given shots to prevent a certain type of flu. All 800 students were exposed to the flu, and 600 of them did not get the flu. Let P represent the probability that the shot will be successful for any single student selected at random from the entire population of 20,000. Let Q be the probability that the shot is not successful. What is the number of trials n? What is the value of r? Since each of the 800 students receiving the shot may be thought of as a trial, then n equals 800 and r equals 600 is the number of successful trials. What are the point estimates for P and Q? We estimate P by the sample point estimate P hat equals r over n, successes over total, so we get 600 over 800, which is 0.75. And we estimate Q by Q hat equals 1 minus P hat, so 1 minus 0.75, so 0.25. Would it seem that the number of trials is large enough to justify a normal approximation to the binomial? Since n equals 800, and P is approximately 0.75, and Q is approximately 0.25, then NP is approximately 600, which is greater than 5, and NP is approximately 200, which is greater than 5. A normal approximation is certainly justified. Find a 99% confidence interval for P. So in the table in the front of your book on the flappy thing, you can see that The critical value for 99% is 2.58. So to find the margin of error, we do 2.58 times the square root of 0.75 times 0.25, all divided by 800, and we get 0.0395. So, since the margin of error is 0.0395, the confidence interval is now 0.75 minus 0.0395 is less than p is less than 0.75 plus 0.0395. So p is between 0.71 and 0.79. So the actual probability is between 71 and 79%. We are 99% confident that the probability a flu shot will be effective for a student selected at random is between 0.71 and 0.79. Interpreting results from a poll. So this is what I was talking about earlier. This you'll see more than anything else. It's when you see a poll, this is kind of what you're looking at and what you can think about. Newspapers frequently report the results of an opinion poll. In articles that give more information, a statement about the margin of error accompanies the poll results. In most polls, the margin of error is given for a 95% confidence interval. And I looked at a whole bunch and they don't specifically state it, so I think it's just the way they usually do things as a 95% confidence interval. So, general interpretation of poll results. When a poll states the results of a survey, the proportion reported to respond to the designated manner is p hat, the sample estimate of the population proportion. The margin of error is the maximal error E of a 95% confidence interval for P. A 95% confidence interval for the population proportion P is poll report P hat minus margin of error E is less than P is less than poll report P hat plus the margin of error E. So what you'll usually see on a poll is they'll give results usually between two things, one being a success, one being a failure. And then in like the lower corner somewhere, you'll see like plus or minus 3.8% or something like that. So that's the margin of error, and so the percent you see is not the population, but it's the point estimate. So p hat. Sample size for estimating p. Suppose you want to specify the maximal margin of error in advance for confidence interval for p at a given confidence level c. What sample size do you need? The answer depends on whether or not you have a preliminary estimate for the population probability of success p in a binomial distribution. N is going to be equal p times 1 minus p times z sub c over e squared if you have a preliminary estimate for p. So if you have a point estimate, you can use that. If you don't have a point estimate, then n equals 1/4 times z sub c over e squared. So where they get 1/4 from is that's the highest that p times 1 minus p can be, but where p is 50%, so 1 minus p would also be 50%. So that would give you 0.5 times 0.5, which is 0.25, which is 1/4. If n is not a whole number, increase n to the next higher whole number. Also, if necessary, increase the sample size to ensure that both NP and NQ are both greater than 5. So don't round n, bring it to the next higher number, and make sure it meets both NP and NQ greater than 5. Note that n is the minimal sample size for a specified confidence level and maximal error of estimate. So it's not all you need, but it's the minimal that you need, so you can go above. A company is in business of selling wholesale popcorn to grocery stores. The company buys directly from farmers. A buyer for the company is examining a large amount of corn from a certain farmer. Before the purchase is made, the buyer wants to estimate P, the probability that a kernel will pop. Suppose a random sample of n kernels is taken and R of those kernels pop. The buyer wants to be 95% sure that the point estimate p hat equals r over n for p will be in error either way by less than 0.01. If no preliminary study is made to estimate P, how large a sample should the buyer use? So this company wants to know if it's selling bags of popcorn, will the margin of error be between will the margin of error be just 1% from the amount that pops? So the amount of popcorn that pops doesn't fluctuate all that much. In this case, we use equation 22 with the critical value at 95%, which from this table we can see is 1.96, and E equals 0.01, which is the margin of error the buyer wanted. So N equals 1/4 times E sub C over E squared, so 1/4 times 1.96 over 0.01 squared. So 0.25 times 38,416, which is 9,604. The buyer would need a sample of 9,604 kernels to be 95% certain that the margin of error wouldn't fluctuate by more than 1%. Preliminary study showed that P was approximately 0.86. If the buyer used the result of the preliminary study, how large of a sample should he use? So a preliminary study could mean that the buyer grabs a bunch of their kernels and pops them on his own and gets that 86% of them were popped. So now it can be a little bit more precise. So in this case, we use equation 21 with P being about 0.86. Again, from table 7.2, the critical value is 1.96, and from the problem, E equals 0.01. N equals P times 1 minus P times E sub C over E squared. So 0.86 times 0.14 times 1.96 over 0.01 squared gives us 4,625.29. So the sample size should be at least 4,626. Remember, we went up to the next number. This sample is less than half the sample size necessary without the preliminary study. So if you have a point estimate, the sample size that you need will be much, much lower. Now time for the sponge. In a marketing survey, a random sample of 1,001 supermarket shoppers revealed that 273 always stock up on an item when they find that an item at a real bargain price. Let P represent the proportion of all supermarket shoppers who always stock up on an item when they find a real bargain. Find the point estimate for P. For part B, find a 95% confidence interval for P. Give a brief explanation of the meaning of the interval. And part C, as a news writer, how would you report the survey results on the percentage of supermarket shoppers who stock up on real bargain items? What is the margin of error based on a 95% confidence interval? Alright, that's it for the lesson. Once again, please make sure to take notes on the entire lesson, take a picture of everything, submit it all to Google Classroom, and have a good night.